All right, so in the last video, we saw that if you apply the principle, if you apply Newton's second law to a system of particles, then Newton's second law looks like this. And that it says that the net external force is equal to the rate of change of momentum, total momentum of the system. And so if the net external force is equal to 0, then the total momentum of the system is conserved. All right, so this has many applications. The applications can be mostly classified into two categories. Situations where objects break up into multiple pieces, which we are just going to call explosions, or situations where objects slam into each other, collide with one another, and those are called collisions. So we are going in both of these situations, the external forces acting on the system are very small in comparison to the internal forces acting on the system. So for example, if you consider a grenade exploding, the forces that push the various parts of the grenade apart are very large, and those are all internal forces. What about the external forces? So there is gravity, there might be a little bit of friction, air resistance as the pieces are beginning to fly out. So those external forces are negligible in magnitude compared to the internal forces. And so you can forget about the external forces and say that there is no net external force. So in that case, momentum is going to be conserved. And the same thing applies to collisions. So if you have two objects colliding, the forces that they apply on each other when they collide are very large compared to external forces like friction, air resistance, gravity, and stuff like that. And so you can just ignore the external forces again. And in the absence of external forces, we know that the momentum of the system is going to be conserved. So momentum is conserved for explosions and collisions. All right. Let's try this conceptual question. So please read this question and see if you can come up with an answer. Pause the video if you need to think about it. And only once you've come up with an answer, then resume the video to see how I answer it. Okay, so a ball is thrown vertically upwards. At which point in its motion is the momentum conserved? The correct answer is none of these. The momentum of this ball is not going to be conserved. Why is that? Because remember the equation, net external force is equal to the rate of change of the total momentum of the system, right? Momentum is conserved only when the left-hand side of this equation is 0. The net external force is 0. Can we say that the net external force on the ball is 0? The answer is no. If you just treat the ball as a system, then it has an external force on it, gravity. If you take air resistance into account, then that's another external force. So the net external force on this system is certainly not 0, so there's no reason for momentum to be conserved. The momentum of the system will change, and the rate of change will be given by Newton's second law, right? Okay. There is a subtlety here. We are treating the ball as our system. However, we could have also done the following. So here is the ball and here is the earth. Obviously, this is not drawn to scale. Suppose you decide to expand your system so that it includes both the ball and the earth. In this expanded system, the force of gravity felt by the ball is an internal force, right? You know that by Newton's third law, there is a force that's being felt by the earth as well. Though the earth is so large that this force from the ball hardly has any effect at all. So if you expand your system to include both the earth and the ball, then then the net external force on the system is 0, because these two forces, gravity just becomes an internal force in that case. So in that case, the momentum of the ball plus the earth will be conserved, right? However, this question is just asking for the momentum of the ball. And the momentum of the ball, if you take the ball to be your system, then there is an external force acting on the system, and so the momentum of the ball will not be conserved. So whether momentum is conserved or not really depends on what you are considering your system, right? And the key question is there an external force on your system? If there is, is there a net external force on your system? If there is a net external force, then the momentum will not be conserved. All right. Let's do an example problem. So please try this problem on your own first, and then you can look at how I approach it. So this is an example of an explosion. Right? So you've got a 10 kg object which explodes into two fragments, and one of the fragments is 8 kg and it moves due east with a velocity of 4 meters per second. So this is what it was before, and this is what it's, maybe I'll just draw it over here. So this is you just had one object sit at rest, and then after the explosion you have two objects, one of them heading off to the east and this has a mass of 8 kgs. It's heading off to the east with a velocity of 4 meters per second, and this has a mass of 2 kgs obviously, and the question is what velocity does it have? So what you do in conservation of momentum problems is that you always set the total momentum before the explosion or collision equal to the total momentum after the explosion or the collision, right? Because momentum is conserved. So what was the total momentum before? It was just 0 because nothing was moving. So the total momentum before was 0. What is the total momentum after the explosion? So the momentum of the 8 kg piece is going to be 8 times 4. I'm not writing units, just it's kg and meters per second. And what is the momentum of the 2 kg piece? So the momentum of the 2 kg piece would be 2 multiplied by the unknown velocity of the 2 kg piece, right? So now we can solve for v, and so v is clearly minus 16 meters per second. What is the minus telling us? When we took the velocity of the 8 kg piece to be plus 4, we are implicitly choosing the sign convention that right is positive. So that's why we took the velocity of the 8 kg piece to be plus 4, right? So the math is telling us that the 2 kg piece is moving in the opposite direction, and so we got a negative sign for the velocity of the 2 kg piece. So the answer to the question is that the 2 kg piece is moving with a velocity of 16 meters per second to the west. And to summarize, the way we did that is we set the total momentum before equals the total momentum after. This is pretty much all you do in all conservation of momentum problems. All right, let's try. So this is slide 12. Let's try the second part of slide 12. So this is asking for the average force on each fragment. How would we find the average force on the fragment? So for that, we can use an equation that we discussed in the last video. The average force, F average, from the momentum from the impulse momentum theorem, F average multiplied by delta T is equal to delta P. Right? So we can use this equation to find the average force. So let's consider the 8 kg piece first. The average force felt by the 8 kg piece would be the change of momentum for this piece divided by the time it took for that momentum to change. So, what was the final momentum of the 8 kg piece? It was it was 8 times 4, which is 32 kg meters per second, minus what was the initial momentum? Initial momentum of that piece was 0 because it was at rest, divided by the time over which that change happens. So that's 32 milliseconds. So this is kg meters per second, and this is seconds. And so this comes to 1000 kg meters per second square, which is 1000 newtons, right? And the plus sign is telling us that the force points to the east. Okay, let's do the 2 kg piece now. The F average would be, again, the same equation, delta P divided by delta T. So that's going to be the final momentum of the 2 kg piece right after the explosion was, in our sign convention, 2 times negative 16. So in other words, it was minus 32. And the initial momentum of the 2 kg piece was 0. And then you divide that by the delta T that's provided, 32 times 10 to the negative 3. Again, kg meters per second over here and just seconds over here. So what does this give us? This gives us exactly the same thing, but with opposite sign, minus 1000 newtons, which means that it's to the west. So both of these pieces feel exactly the same force, right? And I hope you're not surprised that the force comes out to be the same, because you've already seen that happen in Newton's third law, right? So basically we just showed that Newton's third law is true. The force exerted by one piece is the action, on the other is the action, and the reaction is the force exerted by the other piece back on the first piece. That's the reaction. Newton's third law says that for every action there's an equal and opposite reaction. Now, there is a deep connection between Newton's third law and conservation of momentum. In fact, Newton's third law is true because of conservation of momentum. That is the reason that Newton's third law is true. Right? In fact, there are certain situations which we are not even going to get close to in Physics 1 and Physics 2, but there are certain examples where Newton's third law is violated, but conservation of momentum is not violated in those cases, right? So conservation of momentum is the more fundamental thing. Newton's third law is a consequence of conservation of momentum. All right, okay. Let's move on to collisions. So collisions, you all know what collisions are. Collisions are when two objects collide. It's as simple as that. There are three types of collisions, okay? The most common type of collision is called the inelastic collision. So in an inelastic collision, the definition of an inelastic collision is that kinetic energy is not conserved. So you all know the formula for kinetic energy. It's half mv squared, right? Suppose you calculate the total kinetic energy of the two objects just before they collide, and then after the collision, they have new velocities. You calculate the total kinetic energy of the two objects after the collision, right? You will find for an inelastic collision that after the collision you have less total kinetic energy than you had before the collision. And why do you have less kinetic energy after the collision than before the collision? Energy is always accounted for, right? Like money. So if energy has disappeared, then it must have gone somewhere. So where did that missing energy go? The answer is it went into work and heat, because when the objects collided, they deformed, right? And typically the forces of deformation are non-conservative forces. And so the work done against these non-conservative forces is converted into heat, and it's lost from the system. And that is why when you calculate the kinetic energy after the collision, you find that it's not equal to it's less than the kinetic energy before the collision. So in an inelastic collision, kinetic energy is not conserved because some energy is converted into heat as the objects get bent and deformed, right? That's an inelastic collision. Uh, An extreme case of an inelastic collision is called the completely inelastic collision. So in a completely inelastic collision, the two objects that are colliding just get stuck to one another, right? And they just sort of become one object after the collision, right? So one example of that, a simple example of that would be if you take two balls and stick some Velcro on them, and then make them collide, then the balls will stick together, right? And that's an example of an inelastic collision. Another example would be, you might have seen these terrible car accidents where the two cars collide at very high speeds and then they sort of fuse into one wreck. That would be an example of completely inelastic collision. So completely inelastic means that the two objects collide, two objects that collided fuse together and are stuck after the collision. So there is only one object after the collision, right? And obviously, kinetic energy is not conserved in a completely inelastic collision. The third type of collision, which is a very special case, is the elastic collision. You can probably guess what an elastic collision is. In an elastic collision, the kinetic energy is conserved. That's the definition of an elastic collision. So if the total kinetic energy before the collision equals the total kinetic energy after the collision, then we call that an elastic collision. So how is the kinetic energy conserved in an elastic collision, whereas it's not conserved in an inelastic collision? Let's look at a simple example of an elastic collision. Suppose you have two tennis balls which slam into each other, right? Now tennis balls are pretty elastic in the sense that if you squeeze a tennis ball, it'll just come back to its original shape immediately, right? If you squeeze a tennis ball, it'll deform for a moment, but it'll come back to its original shape the moment you let it go. So when two tennis balls collide, they might temporarily deform, right? But then the next moment, they just spring back to their original shapes. So the forces of deformation in the case of the tennis ball or rubber balls are elastic forces, are conservative forces. They're not non-conservative forces, right? So the work done against a conservative force is just stored as potential energy, and it's not lost as heat. So the next instant after the collision, it's again reconverted back into kinetic energy, right? So that is how kinetic energy is conserved in an elastic collision. So just to summarize, momentum is conserved in all collisions, right? Kinetic energy might or might not be conserved. If it's not conserved, then the collision is called an inelastic collision. And if kinetic energy is also conserved together with momentum, then the collision is called an elastic collision. And among inelastic collisions, there is a classification. You have inelastic collisions, the ordinary inelastic collisions, where kinetic energy is not conserved and the objects don't stick together. If the objects stick together, we call that a completely elastic collision. So please make sure that you understand the three types of collisions, right? Okay. And also I want to emphasize that most collisions are inelastic collisions. Elastic collisions are a very special category of collisions. So you cannot just assume that a given collision is an elastic collision, right? Unless you have some evidence, unless the problem says that it's an elastic collision or that kinetic energy is conserved, you cannot just a priori assume that a collision is an elastic collision, because most collisions are actually inelastic collisions. All right, so let's try this little question over here. I asked this as a top hat question in class. Please see if you can answer it yourself and pause the video while you're thinking about it. So in collisions, which of the following is true? The correct answer is that Correct answer is C. Momentum is always conserved, but kinetic energy is sometimes conserved. All right. Okay, so what we're going to do next is we will just look at a few examples of problems on collisions. I have one fully worked out example over here. You can just do this on your own. I usually have the class work through this example uh, as a top hat example. Um, give this a try. Pause the video and give this a try and see if you can work it out. And then look at how I do it. Okay. So this is the example on slide 16. All right, so a ball of mass m and speed v collides with another ball of mass 2m at rest. The first ball rebounds with speed v over 2 in the opposite direction. What is the speed of the second ball? So this is a collision, so you know that momentum is conserved. So to do conservation of momentum problems, you always do total momentum before equals the total momentum after. So the total momentum before. So what had momentum before the collision? So we have the ball of mass m. So you just have the ball of mass m, which is moving with a velocity v, and the ball of mass 2m is just sitting here, not moving. So the total momentum before the collision is mv. The 2m mass does not have any momentum. And whenever you're doing momentum, and you've probably noticed this by now, but it's worth pointing out, whenever you're doing problems with momentum, it's very, very important to keep track of directions because momentum is a vector, right? So we are keeping track of directions in this problem by using the sign convention that right is positive. That's our sign convention. So that's why we gave the mv a positive sign. All right, so we know the total momentum before the collision. That has to equal the total momentum after the collision. So after the collision, both the masses have momentum. So the m is moving back at velocity v over 2, and the 2m is moving in some direction. We know even without doing any calculations, you can tell that it has to move to the right because the total momentum before the collision was to the left. So something has to move to the right. Otherwise, momentum conservation would clearly be violated. So you know that capital V, let's say that capital V is the unknown velocity of the 2m mass after the collision. You know that it will be to the right. Okay. So let's set up the total momentum after the collision. So it's just going to be m times negative v over 2 plus 2m times capital V. Capital V is unknown. And so let's see. So this is 3mv over 2 is equal to 2m capital V. And just as expected, capital V is coming out to be a positive number. And so capital V is equal to 3v divided by 4. So B is the correct answer. When doing this problem in class, a common mistake that a lot of students make is they forget about this negative sign. That is extremely important because momentum is a vector quantity. So you have to keep track of the direction of momentum. All right. Let's try one more example. So this is the example on slide 17. Oops. So this is the example on slide 17. It says that a large ball of mass 10 kgs is moving upwards with a velocity of 3 meters per second, and a small ball of mass 1 kg, so here's our large ball, it's moving upwards with a velocity of 3 meters per second, and a small ball of mass 1 kg is moving downwards with a velocity of 3 meters per second. After the collision, the large ball continues to move upwards with a slower velocity. So this is before. And after the collision, the large ball continues to move upwards with a slower velocity of 1.91 meters per second. And you have to find out what is the velocity of the smaller ball. So we are going to do this problem in exactly the same way that we did the last one. So I would highly recommend trying to figure it out yourself and see if you can get the answer. Okay, so let's just work it out. So we're just going to do total momentum before equals the total momentum after. So the total momentum before the collision would be, let's choose a sign convention. Let's just choose up is positive. Our sign convention is upward is positive. So the total momentum before the collision would be 1 multiplied by minus 3 for the small ball plus 10 multiplied by 3 for the large ball. Notice that I'm following the sign convention for the velocities. Okay, and the total momentum after the collision would be 1 multiplied by v, which is the unknown momentum, unknown velocity, plus 10 multiplied by 1.91. Okay, so let's work this out. So this is 30 minus 3 is 30 minus 3 is 27 is equal to v plus 19.1. So v is equal to 7.9 meters per second. Okay. V is equal to 7.9 meters per second. So that is the velocity, and it's coming out to be positive, which confirms what we already know from intuition, that the ball has to move upwards. So the ball is moving at a very high velocity now, like almost 8 meters per second. The small ball, it was moving at 3 meters per second. Now it's moving upwards at 8 meters, at a tremendously high velocity of 8 meters per second, tremendously high compared to its initial velocity, right? It's more than double its initial velocity. So let me show you an example of this. I have a nice video in the PowerPoint. I probably won't be able to show you very nicely on here, but I would recommend just clicking on the video and watching it on your computer if possible. All right, so she's showing us three balls which don't bounce that much, but she's stacking them one on top of the other like this, and watch what happens. Do you see how the smallest ball just shoots up to a tremendously large height, which means its velocity after the rebound is very, very large. We saw this happen in the example that we just did, and you should also watch this entire video because it's great, and she also explains this, and there is a really, really fascinating application of this idea to supernova explosions. So supernova explosions are when stars explode at the final stage of their lives and die in incredibly powerful explosions. This little fact plays a role in a supernova explosion. So she talks about it briefly in her video. So I'd recommend watching the video. All right, I'm going to show you another thing. Okay, so let's watch this guy. Did you see how this ball shoots up to a tremendously large height? So this is absolutely crazy. I find it fun to watch, so I'll just click this one more time. The ball just shoots up to a tremendously great height, right? Um, let's, can you, based on what we just did, can you guess what's going on over here? Like, why does the ball shoot up to such a tremendous height? Well, the answer has to do with the fact that the person who's doing the trick is pretty large, right? And so when the person jumps into the water, he creates a pretty large cavity inside the water, right? And notice that when he jumps into the water, he holds the ball a little bit above him. So he gets into the water and creates this cavity first, and the ball has not yet reached the water, right? Now, whenever you create a cavity like this in water, what happens is that the water starts rushing in to fill this cavity. And all this water rushing in at once has the effect of sending a large jet of water in the upward direction, right? So you have a huge jet of water which is just beginning to shoot upwards, and the ball which the guy was holding right above his stomach smacks into that upward moving large jet of water, right? So the water has a very large mass, and so that's comparable to the problem that we just did. So our small mass was 1 kg and the large mass was 10 kg, remember? So so the large amount of water which is on its way upwards has a very large mass, and when it smacks into the ball with a small mass, it gives it a lot of momentum, right? Momentum is mass multiplied by velocity. So the small mass acquiring a lot of momentum shows up in a tremendous increase in velocity. And that's why the ball shoots up with a very high velocity. So that's just an application of this example. That's just an illustration of this example that we did earlier. Okay. Now, I'll just mention one other thing here. This principle, the fact that if you create a cavity inside water, then the water rushes to fill up that cavity and produces an upward moving jet of water, has many other applications as well. One application is a torpedo, which is used to sink ships. So here's our ship. Now, if you fire a missile into a ship, a torpedo into a ship, it might not be a good idea to hit the ship directly. Why? Because ships are often very well reinforced, and so if you damage the ship to some extent, it might still survive because it's very well reinforced. A better way of destroying a ship is to have a torpedo which comes in and explodes somewhere underneath the ship. So it doesn't even come in contact with the ship. It creates a huge explosion somewhere underneath the ship, right? That creates a huge bubble, a huge cavity in the water just underneath the ship, and the cavity fills up with water, just like our last example, creates a very fast moving jet of water with tremendous energy moving upwards, and that is often sufficient to snap a ship in two. All right, okay, so that's just an application of that. Okay, I have one more problem over here, which is slide, so this problem, which is slide 18. I think you can probably set this problem up the same way we set up the other ones and work it out for yourself. Um, all right, so these were all one-dimensional problems. Let's see what happens in a two-dimensional conservation of momentum problem, a two-dimensional collision problem, right? So two-dimensional problems in principle are quite similar to one-dimensional problems, except that you have to just apply conservation of momentum along the x direction and along the y direction. That's pretty much all that you do. So let's see if we can work this problem out. So we have two masses. One of them is moving along the x-axis and the other is moving along the y-axis. They collide at the origin, and then they stick together and start moving in this angular, into kind of like in this direction indicated by the arrow. So you have to find the final velocity of the two masses, of the combined mass, and the angle that the velocity makes with respect to the x-axis, right? Okay, so what you do is you again just, this is a collision, so the total momentum before will be equal to the total momentum after. Can you tell me what kind of collision this is? The answer is it's a completely inelastic collision because the two masses stick together after the collision, right? So let's apply conservation of momentum. Since this is two-dimensional, we are going to apply conservation of momentum along the x direction and also along the y direction. And any momentum vector that you see when you're doing this, you want to first break it up into an x component and a y component, and then basically apply conservation of momentum along the x direction with all the x components of everything, and apply conservation of momentum along the y direction with the y components of everything. And that's pretty much all that you have to do. So the total momentum, let's look at all the momentum vectors that we have. Oops. Let's look at all the momentum vectors that we have. So we have the momentum of the small mass, mv, along the x direction, momentum of the large mass, capital M, capital V, along the y direction, and then the momentum of the combined mass. So what is that going to be? That's going to be little m plus capital M times V prime, and that is in this direction, northeastern direction, basically. Okay. So let's break up this momentum into two components. So we can have one component like this and another component like that. Okay. So this angle is theta. So I should probably write little m plus capital M V prime over here. So the component that's horizontal by SOHCAHTOA is going to be little m plus capital M V prime cosine theta. And this one will be little m plus capital M V prime sine theta. All I did was break up the green vector into a x component and into a y component, right? All right, so now I'm ready to apply conservation of momentum because every vector is either along the x or y direction, or it's been broken up into components that are along the x and y directions. All right. So let's do the x direction first. What is the total momentum in the x direction before the collision? Now the only momentum arrow that I can see in the x direction is the momentum of the little mass. So it's just going to be little m v. That's the total momentum before the collision in the x direction. And let's set that to the total x momentum after the collision. So the only x momentum that I have after the collision is little m plus capital M v prime cosine theta. All right. That's one equation. There are two unknowns here, v prime and theta. So it looks like I have one equation for two unknowns. I just need one more equation. The next equation comes from the y direction. So the total momentum in the y direction before the collision is capital M, capital V. And after the collision is little m plus capital M v prime sine theta. All right. So I have two equations and two unknowns, which means the physics part of this problem is done. I have enough information to solve the problem. Now I just need to algebraically solve these equations and find what the angle is and what v prime is in terms of little m, capital M, little v, and capital V, right? Let's call this equation number 1, and let's call this equation number 2. How do we algebraically solve equations 1 and 2 to solve for v prime and theta? How do we algebraically solve these two equations to get our two unknowns? Think about that for a moment and see if you can come up with a very quick way of solving for theta. Did you figure it out? The easiest way to solve for theta is to divide the second equation by the first equation. I mean, divide the right sides, divide the left sides. If you do that, on the right side, you get everything cancels out and you're just left with tan theta. And on the left side, you're left with little m, little v, capital M, capital V. And so you can easily solve for theta from there. So theta is equal to tan inverse little m, little v divided by capital M, capital V. And you found the angle. And then once you found the angle, you can plug it into either of those two equations and solve for v prime, right? So that's one way of doing it. So the point here is that if you have a two-dimensional problem, you just apply conservation of momentum the same way. Set the total momentum before the collision equal to the total momentum after the collision. But you want to do that with all the x components, and then you want to do that with all the y components, and that will give you two equations from which you can solve for your unknowns. All right. So in the next slide, I have a fully worked example. It's a little complicated, but the principle is exactly the same as the last problem that we just did. So I would recommend working that out on your own. Okay, now I'm next going to talk about one more type of example where you have to apply conservation of momentum and conservation of energy. You have to apply both conservation of momentum and conservation of energy. Now, I'm not going to do this entire problem. I have given plenty of hints on the slide, and I'm sure you can work it out on your own. But I will just basically talk about this problem a little bit, just to show you why you need to apply both conservation of momentum and conservation of energy. But I'll let you try this problem yourself. Okay, so what's happening in this problem? So what's happening is you have basically this arrangement is called a ballistic pendulum. So you have a block of wood and you fire a bullet into this block of wood. The bullet has some initial velocity. Let's just call that V initial. Okay, so what happens? The bullet hits the block and gets embedded in the block, right? And then the bullet and the block both start moving, and eventually they rise up somewhere over here. So now the bullet is embedded inside the block, right? Let me just make that a little more accurate. So just keep the length of the string the same, more or less. Okay, the bullet is now embedded inside the block. Maybe I should just draw it from the same point, so it's going to be clearer that way. Yeah, there. So the bullet is now embedded in the block. The question is, okay, you can easily measure how high, how much does the block rise? And you know the mass of the block, you know the mass of the bullet, you can measure these easily. And you can measure how high the block rises. So from these pieces of information, can you figure out the velocity of the bullet? That's the question. And this particular arrangement was used in the very old days to measure the velocities of bullets, because all of these things are easily measurable. You can measure how high the block rises. You can easily weigh the bullet and the mass and all that and figure out those things quite easily. So using a few easily measured quantities, you can calculate the velocity of a bullet, right? So this was called the ballistic pendulum. All right, so now let's think about this. Now, my first question is, if you calculate so let's call this position number 1. Position number 2 is when the bullet just strikes the block and both the bullet and the block start moving. And position number 3 is when the bullet and the block have gone as high as they will go and are momentarily stopped before it starts swinging down, right? Is it true that the total energy total energy, mechanical energy is what I mean. Mechanical energy just means kinetic plus potential. So I should probably write, oops. So my question is the total mechanical energy at position 1 equal to the total mechanical energy at position 2, at position 3. In other words, can I say, so at position number 1, if we take h equals 0 over here, the bullet just has kinetic energy. It doesn't have any potential energy because potential energy is mgh and h is equal to 0 at the height of the bullet. So at position number 1, we have all the energy is kinetic, the kinetic energy of the bullet. What about position number 3? Nothing is moving because both the bullet and the block are at rest at position 3, and both of them have gone up by a certain height, h. So can I say that the total kinetic energy at position 1 equals the total potential energy at position 3? The answer is no. Why is the answer no? That is because, what kind of collision is this? Think about that and see if you can answer that question. What kind of collision do you think this is, of the 3 types of collisions we've talked about before? The answer is that this is a completely inelastic collision because the 2 objects stick together, right? Is kinetic energy conserved in a completely inelastic collision? No. Kinetic energy is not conserved. And why? Because some energy is converted into heat. So the total energy that the bullet has to start with, some of that is going to go into heat and light and sound. Most of it really goes into heat. So some of the energy will not be mechanical energy, right? And so when you calculate the mechanical energy at position 3, it's going to be less than the total amount of energy, kinetic energy the bullet started out with. So I hope that point is clear. So you cannot set the total kinetic energy. So you cannot do this. This equation is wrong. Half mv0 square is not equal to, this equation with the inequality is correct. Half mv0 square is not equal to little m plus capital M gh. So this equation is not true. This equation is true. You cannot set these equal. Why? Because some energy is lost as heat during the collision. It's an inelastic, completely inelastic collision. So this, you might have at first thought that this would be one way of solving for initial velocity, v0, but it does not work. So how would you solve the problem then? What you can do is you can, let's say that the velocity of the bullet and the block right after the collision is capital V. So let me just draw a velocity vector here. Capital V is the velocity of the bullet and the block right after the collision, right? Can you apply conservation of momentum between position 2 and conservation of energy between position 2 and position 3? Absolutely, because after the collision is over, there is no more non-conservative forces acting, right? So the total amount of energy right after the collision will equal the total amount of energy. The total amount of mechanical energy at position 2 will equal the total amount of mechanical energy in position 3. And so you can equate the energies at position 2 and position 3 but you cannot equate the energies at position 1 and position 3, right? So how would you do this problem? You would break it up into two parts. You can apply conservation of momentum and calculate the velocity of the bullet and the block at position 2, and then you can apply conservation of energy between position 2 and position 3, and then you can solve the problem, right? So on the slide I have a couple of hints which basically walk you through it, and so give this problem a try, and if you have any questions you can feel free to ask me during office hours. All right, the last type of example that we're going to look at is elastic collisions. So for elastic collisions, you have the equation of conservation of momentum as usual. That's true for every collision. But you also have the equation of conservation of kinetic energy. So you have an extra equation for the conservation of kinetic energy. So in this, now notice this. We have a convention here. We have two objects, their masses are m1 and m2. And we say v10 is the velocity of object number 1, the initial velocity of object number 1. v20, so what does v10 mean? Initial velocity of object 1. v1 without a 0 is just the final velocity of object 1. So that's our convention. So v20 would mean the initial velocity of the second object, and v2 would mean the final velocity of the second object, right? So we have two objects of masses m1 and m2, and we know what their initial velocities are. So we know v10, v20. So these are things that we know. What we're interested in finding is what is the final velocity of object 1 and what is the final velocity of object 2. That's what we want to find, right? Now notice that we have two unknowns, v1 and v2, and we have two equations. So one is the equation of conservation of momentum and the other one is the equation of conservation of kinetic energy. When you have two unknowns and two equations, you can easily solve the equations and just directly solve for the unknowns. This is the solution. This looks rather complicated, but it's just a combination of the four unknown quantities m1, m2, v10, and v20, and it gives you the two unknown quantities. So you know v1 final is given by the first equation, v2 final is given by the second equation. So it's just a formula. Okay, there is one thing that I want to emphasize here. Notice that this formula only applies to one-dimensional elastic collisions, right? It does not apply anywhere else. In fact, that is probably the reason why this formula is not given in your textbook. It's a useful formula, but I suspect it's not in your textbook because the authors of the textbook don't want you to go ahead and apply this formula to everything. That's a very common mistake that I find students making. This formula only applies to one-dimensional elastic collisions, right? So unless you know that the collision is elastic, you don't want to apply this formula, right? Okay, so other than that, this formula is rather straightforward. Like if you know that a collision is elastic, and it's one-dimensional, then you don't even need to think about it anymore. You can just do plug and chug and find the velocities of the two objects after the collision using this formula. Let's look at one example of a problem. That's on the next slide. So what's happening here is that you have a probe that's moving towards the planet Jupiter, right? You're given the velocity of the probe. And it rounds Jupiter, it goes around Jupiter and then comes back at a very high velocity, right? You'll find that the velocity is quite large. So you might be wondering, how is this a collision? Like they didn't really slam into each other. So it's not a collision in the way that we have been seeing collisions so far where the objects actually slam into each other, but the objects do interact, and kinetic energy is conserved, momentum is conserved, and so there is no reason why you cannot treat it as a collision, right? It's a bit of an unusual collision because the objects are not physically coming into contact, but they are interacting through gravitational forces, so it can be treated as a collision, right? Okay, so what we have to do here is we have to find the um, velocity uh, of the probe after after the encounter is over. Okay, so let's give this a try and see if we can figure it out. So you have Jupiter moving in this direction. So this is an elastic collision. So we know exactly what we need to do. We need to apply, it's a one-dimensional elastic collision. So we need to apply conservation of, we need to just apply the elastic collision formula. That's really all that we need to do. So this is just a plug and chug problem. So you have the probe coming in. Let the probe be our mass 1, right? And let Jupiter be our mass 2, right? Okay, so there are 4 known quantities and 2 unknown quantities. So the known quantities are m1, m2, v1 initial, and v2 initial. These are our known quantities, and the 2 unknown quantities are v1 and v2. v1 final and v2 final. Which one is the question asking for? We want to know v1 final. So we want to know the final velocity of our probe after the encounter is over. So we don't really care about v2 final. All right, let's fill in whatever we know for the velocities. It doesn't look like the masses are given, all right? So we'll worry about that later. What do we know about the velocities? So v10 is the velocity of the probe before the collision. So it's given that that is 10.5 kilometers per second. Kilometers per second. And v20, the velocity of 2 before the collision, the velocity of Jupiter, is negative 13 kilometers per second. Notice that I am being careful with signs. So I've chosen a sign convention in which right is positive. So that's why I gave v10 a positive sign and v20 a negative sign, right? Negative 13 kilometers per second. All right, so now let's go ahead and plug these in, plug in what we can into the formula for v1. So according to the slide, the formula is m1 minus m2 divided by m1 plus m2, v10, plus 2m2 divided by m1 plus m2, v20, right? Okay, it looks like we have a huge problem because we don't know what the masses are. Can you think of what we can do here? How do we get around the fact that we don't know what the masses are? And let's assume that we are not allowed to look them up. Well, you can think of it like this. The mass of the probe is about the mass of a SUV, right? And the mass of Jupiter is 318 times the mass of the Earth. So the mass of Jupiter is infinitely larger than the mass of the probe, right? So we can use the fact that M2 is way larger than M1. So when M2 is there, M1 is practically invisible. So you can just ignore all these instances of M1 because M1 is negligible in comparison to M2, right? So that simplifies things a lot. So V1 in that case becomes negative V10 because minus M2 divided by M2 is negative 1. So minus V10 plus 2M2 divided by M2 is just 2. So 2 V20, right? And we can just plug in the numbers. So V10, so it's minus 10.5 kilometers per second plus 2 times minus 13 kilometers per second. So 26 plus 10.5, 36.5 kilometers per second. That is the final velocity of the probe. Notice that the final velocity of the probe is almost 4 times, it's close to around almost 4 times its initial velocity, right? So the probe got this enormous amount of velocity just by getting close to Jupiter, right? So a 4 time, so this is, if it's gone up by 4 times, it's like a 300% increase, right? So a 300% increase of velocity, that's like a 900% increase of kinetic energy, because kinetic energy is proportional to the square of velocity. So if you wanted a 900% increase of kinetic energy of a probe, and if you wanted to do it with fuel, you would need an enormous amount of fuel to accomplish that, right? Whereas this probe had to do nothing. It practically got this energy for free by just getting close to a large planet, large object. So this particular thing is called a gravitational slingshot maneuver, and all the spacecraft that have gone very, very large distances, like the spacecraft that go to other planets like Venus or Mercury or Jupiter, Saturn, or even further, all the spacecraft have to use multiple gravitational slingshot maneuvers in order to reach the tremendously high velocities that they need to reach, right? Um, okay, so this is called a gravitational slingshot maneuver. And in the slide, I have a link to a clip from the movie The Martian, which I show in class. And they basically talk about the gravitational slingshot maneuver that was used in the movie. So The Martian is a very good movie. I would recommend watching it if you haven't already. And this clip is entertaining, so you can take a look at it. All right. I have another plug and chug problem on the next slide, which you can try on your own. A couple of them, actually. Okay, so we're going to stop this video over here. In the next video, we're going to talk about the last important topic in this chapter, which is center of mass.